Okay, so if you're following along with our note packet that we've been using in class, this one's dealing with some negative exponents. And we just finished up some work with exponential growth and decay. So we're kind of going to go back to that for a second. And for the questions here, you're going to have to refer to your note sheet. I'll be reading those to you, but as you can see, there's no actual questions on the board here. So the function y equals 185 times 1.13 to the x can be used to model the average salary for a professional baseball player in the United States in thousands of dollars since 1980. So the first question on our note packet says, what year is represented by an x value of 0? So if x were 0 here, that would actually be our base year of 1980. So for letter A, if you're following along with the notes, that's 1980. Okay? In letter B, it says, what year would be represented by an x value of 7? So if I changed x to 7, that would be 7 years from 1980, and we would be at 1987. Letter C says, what value should you use to find the average salary in 1992? So if we want to find 1992, we know that's 12 years from 1980, so we would use an x value of 12. Now we get into a little bit more difficult problems here. So letter D says, what was the average salary in 1992? So if we want to use our function and we want to find the average salary in 1992, we just figured out that our x value, which stands for our time period, is going to be 12. So all we would do is plug into our calculator, and let me pull up the calculator here for you to see that. We would just plug in 185 times b, which is our growth rate, 1.13, to the, and then again, since it's 12 years later, we would take it to the 12th power. And we would get an answer of 801.89 if we're rounding it. So they want this in thousands of dollars, so we actually wouldn't round that. So this is 801,887. So 801,000, because it's in thousands, 887. So according to this formula, we're looking at an average salary of just over $800,000. Now, here's the key to this section. Letter E says, what x value should you use to find the average salary in 1979? So that's where we would learn that if I want to find a year prior to 1980, I'm going to have to use an exponent, so of a negative value. So x would be -1. Lastly, it says estimate the salary in 1967. So if we want to do that, I'm just going to kind of sketch here that we're doing 1967. And then here's our equation right here. Y would be equal to 185 times 1.13 to the, and now here's 1980, and we want to find 1967, which is 13 years prior to 1980. So for our exponent, we'd actually be using -13, and that should give us the salary for 1967. So we just use our calculator one more time. We're going to get 185 times 1.13 to the -13th. Okay, and there's our answer, $37,770. So we'll just put that here, $37,770. Okay, so basically, if you're still filling in the note packet, what we're looking at here, sometimes exponential functions model change in quantity over time. So we have time on the x-axis and the change in quantity here on the y-axis. And what we're looking at is, this is point 0. This is where we start, okay? And in our problem, this is actually the graph of our problem, we said, well, the base salary in 1980 would have been 185,000. As you can see, just a little bit more than 185 on our, or 181 on our scale. So that's going to be our y-intercept. Now, that shows a 13% growth over time. But if we look prior to 1980, we can see that the salaries were lower, and we would be using negative x values. Still following along in the note packet, we're going to go ahead and try example number 1 now. And example number 1 basically says that in the year 1997, there were 6.4 students for each computer in the U.S. But by 1998, this number had decreased to 5.9. So there were less students per computer. Nowadays, it's probably, most districts want to go 1-to-1, or a lot of places want to have one student per computer. So, but, back in 1998, these were the ratios that we were dealing with. So if I want to figure out an exponential function, well, here we go. The same formula applies. Y equals AB to the x power. So all we need to plug in is our initial value and also our growth or decay rate. Now in this case, since it's decreasing, we're going to get a decay rate. The issue is, as most students would notice, there's no percentage in this problem. So we actually have to figure it out ourselves. Now a lot of students, okay, we can pick these two numbers and we know to get a percentage we're going to have to divide them, but the issue is do you divide 6.4 by 5.9? Or do you divide 5.9 by 6.4? Well, the correct answer would be, since we're decreasing, we're going to want a b value that's less than 1, and the only way to do that is to take the smaller number divided by the larger number. So here's our decay factor, so I'm going to write that as b is equal to, because that's going to go in here, we're going to get 5.9, and we're going to divide that by 6.4. You can go ahead and do that on your calculator, but you actually get about 0.92. Okay, so that's going to go in for B, and since it's written from a 1997 standpoint, our initial value is 6.4, and that's decreasing down to 5.9. So our equation is going to be y equals 6.4 times 0.92 to the x. Okay, and now it says use the equation in part A to estimate the number of students per computer in 1994. So take a guess right now. Would you expect that to be larger or smaller than these numbers? Well, 1994 is prior to either of the years we're dealing with, so obviously we're going to have to deal with a negative exponent. So y is equal to 6.4 times 0.92 to the, now this equation was written for 1997 data. 1994 is 3 years prior, so we need to take it to the negative third. Plugging that in our computer, or I'm sorry, our calculator, gives us 6.4 times 0.92 to the negative third. And that gives us 8.2. So there were approximately 8.2 students per computer in that year. Now, the last thing we're going to be doing is just looking at some exponent rules, and we're going to do that in a subsequent video. So if you don't need any help on just the exponent rules, you can go ahead and stop now. If you do, make sure you look for the next video.